To recreate the reaction that powers the sun, scientists have to heat hydrogen gas past 100 million degrees Celsius, more than 6 times hotter than the core of the sun itself. At that temperature, matter stops behaving like a gas, a liquid, or a solid. It turns into plasma, a chaotic, superheated soup of charged particles moving fast enough to destroy almost anything it touches. And here's the problem nobody can get around. There is no material on Earth that can physically hold it. Not steel, not ceramic, not any alloy ever engineered in a lab. The instant solid matter touches plasma at that temperature, it vaporizes. It doesn't matter how thick the wall is or how advanced the coating is. Physical contact is not an option. So if you want to build a star on Earth, you can't build a container for it. You have to build a cage made of nothing but magnetic force. That's exactly what engineers at the Institute of Plasma Physics, or ASIPP, in Hefei, China, just did. They completed full-load testing on a superconducting magnet weighing 582 metric tons, the largest fusion magnet ever built in human history. Its entire job is to hold a 100 million degree artificial sun in place without ever letting it touch a wall. Here's the thing about the race toward clean energy right now. Most people don't realize how fast it's actually moving, and machines like this one are the reason. Fusion research crawled along for decades with barely any visible progress. Now, breakthroughs like this magnet are landing every year or two. If you want to keep track of where this technology goes next, hit like and subscribe now, because the story is only picking up speed from here. Building a magnet this large isn't just a bigger version of what came before. It's the specific engineering step that has to happen before fusion can stop being a laboratory experiment and start being an actual power source for civilization.
So, how do you actually build a magnetic cage strong enough to do that? The machine at the center of this is called a tokamak, a donut-shaped vacuum chamber wrapped in rings of massive magnetic coils. Plasma is made of charged particles, and charged particles follow magnetic field lines the way a train follows a track. So instead of touching a wall, the plasma gets bent into a tight, spinning donut shape that floats in mid-air, held just fractions of an inch away from the solid metal surrounding it. The field has to stay smooth and consistent all the way around that donut, because even a small gap or a weak spot is enough for the plasma to drift and touch the wall. Nothing touches, nothing melts. Now, here's where it gets interesting. In fusion, bigger isn't just a little better, it's exponentially better. There's a basic geometric rule at play. As you scale up a reactor, the volume where fusion actually happens grows faster than the surface area where heat leaks out. So a bigger, stronger magnetic cage traps heat far more efficiently than a smaller one. Push the magnetic field higher, and you're essentially squeezing the plasma tighter, giving hydrogen atoms more chances to collide before any heat escapes. That's why the size of this coil matters so much. It's D-shaped, built from superconducting material, and it generates a magnetic field of 6.5 Tesla, more than 4 times stronger than the magnet inside a hospital MRI machine. And it doesn't work alone. 16 of these coils are arranged in a ring inside a facility called the Burning Plasma Experimental Superconducting Tokamak, BEST for short, and together they form one continuous magnetic cage strong enough to contain the entire reaction. Just look at the scale of a single one of these coils. Standing 21 meters tall, about 69 feet, roughly the height of a 7-story building, one coil weighs 582 metric tons. That's the equivalent of nearly 300 pickup trucks compressed into a single ring of metal and superconducting cable. And this isn't just the biggest magnet China has ever built. Compare it to the equivalent coils being built for the International Thermonuclear Experimental Reactor, known as ITER, a fusion project in France backed by dozens of countries. This single Chinese coil holds 1.3 times the volume and stores 3 times as much magnetic energy. winding hundreds of tons of superconducting cable into a precise D shape without a single flaw, then casing it in steel built to survive temperatures near absolute zero, is as much a manufacturing achievement as it is a physics one. None of this works without solving one more problem: electrical resistance. Normal wire loses huge amounts of energy as heat the moment electricity flows through it. Superconducting cable, in this case made from niobium tin, carries electricity with zero resistance, but only if it's cooled to nearly absolute zero, around -269 degrees Celsius. Once the magnet is charged and running that cold, it holds its magnetic field using barely any additional power, which is exactly what makes long-term fusion energy realistic instead of a battery-draining fantasy. A reactor that needs constant, massive power just to keep its own magnets running would defeat the entire purpose of generating electricity in the first place. And here's what sets this magnet apart from other fusion projects around the world. International megaprojects have been slowed for years by supply chains stretched across a dozen countries, each one waiting on parts from somewhere else. This magnet didn't have that problem. Every raw material, the ultra-low temperature steel casing, the insulation, and the superconducting cable itself was designed and manufactured entirely inside China, under a program whose official name is the Comprehensive Research Facility for Fusion Technology, or CRAFT for short. China's dedicated effort to build and test fusion components domestically. No cross-border delays, no waiting on another country's factory. One supply chain, start to finish. That kind of control doesn't just save time, it means the entire production process, from raw material to finished coil, can be refined and repeated for the next reactor.
So why go through all of this trouble? Because of what fusion actually runs on. These reactors fuse together isotopes of hydrogen, mainly deuterium and tritium, and deuterium happens to sit in nearly unlimited supply inside ordinary seawater. A single bathtub full of seawater contains enough deuterium to generate roughly as much energy as burning 300 metric tons of coal. Multiply that across every ocean on the planet, and you're looking at a fuel source that could power human civilization for millions of years without running out. There's no drilling, no mining, and no geopolitical scramble over where the fuel happens to be buried. It's already dissolved in water, everywhere on the planet. Unlike traditional nuclear fission, fusion physically cannot melt down. If the magnetic field cuts out or the fuel supply stops for any reason, the plasma cools and shuts itself off within milliseconds. There's no chain reaction to run away with. On top of that, fusion produces zero greenhouse gas emissions and none of the long-lived high-level radioactive waste that fission plants leave behind for thousands of years. It solves the safety problem and the waste problem at the same time, which is exactly why so much engineering talent is pouring into it right now. Think about what unlimited, low-cost baseline power actually unlocks. Large-scale ocean desalination becomes affordable enough to ease regional droughts. Heavy industrial manufacturing gets access to power that doesn't fluctuate with the weather. And the massive data centers now training artificial intelligence, which already pull more power every year than the one before, could run on clean electricity without straining local power grids the way they do today. This isn't just about keeping the lights on. It's about removing one of the biggest constraints on what humanity can actually build.
So, where does this magnet actually fit in the timeline? The best facility in Hefei is built to be the bridge between decades of academic fusion physics and an actual working power plant. Engineers are targeting completion of the first full plasma assembly by 2027, and once it's running, the goal is to reach what's called a burning plasma state, a self-sustaining reaction with a target energy gain of 5 times the power put in, written as Q equals 5. That number is the difference between a science experiment and a machine that actually produces usable power. Cross that threshold, and the design work shifts from proving the physics to engineering an actual commercial power plant around it. From there, the roadmap points to around 2030, when engineers expect to generate the world's first pilot electricity directly from a controlled fusion device, not a lab demonstration, actual electricity produced by fusing hydrogen fed toward a real grid. That single milestone would move commercial fusion power from theoretical to operational. For most of the last century, fusion was the joke that was always 30 years away. But a 582-ton ring of magnetic steel just turned on in Hefei, and with it, humanity stopped studying the power of the stars and started building the grid that will actually run on them.